chapter 5 right now, talking about other types of chemical reactions, aqueous reactions specifically. Now we're going to talk about different types of equations. So representing molecular, ionic, and net ionic equations. So first off, we'll talk about molecular equations. And remember, a molecule means stable group of atoms. And looking at this equation here, it's lead 2 nitrate aqueous with 2 potassium chlorides aqueous forms lead 2 chloride solid plus 2 potassium nitrates aqueous. So this equation here, and this is the molecular equation, and it kind of, if I look at this, I kind of imagine myself making the lead nitrate. So I'll take the solid lead nitrates, usually with a nickel spatula, and pushing it into a beaker, filling it up with water, mixing it up. Same thing with the potassium chloride, of course, using different spatulas. And then I mix them together, and down falls the lead chloride, and then there's potassium nitrate left in solution. So that's kind of what I see when I do this, when I look at this equation. And this is a molecular equation. So remember, molecule means stable group of atoms. So they're all hanging out together, and it also kind of tells you how you made it. So this is typically how things are written. Sometimes you can see what's called the complete ionic equation. And this is, it's usually not listed this way, but it can be. And this gives you lots and lots of information. So in this complete ionic equation, you have the lead plus 2 ion in the aqueous phase, and 2 nitrate anions in the aqueous phase. Get your thing. Plus 2 potassium ions in the aqueous phase, and 2 chloride anions in the aqueous phase. Thank you. Yields the lead chloride precipitate plus 2 potassium ions aqueous and 2 nitrate anions aqueous state. So this is kind of like, I don't know, you ever read books you didn't like? I didn't like Steinbeck and Melville. What?
The Of Mice and Men?
I didn't read that one. I read Grapes of Wrath.
Okay. Mice and Men was pretty good.
Yeah, I was called Lenny when I was a kid, though. So always pick on the big blonde guys, I guess. But I mean, lots and lots of detail. What I'm going at is like lots and lots of details, like Steinbeck and Herman Melville. So, but if you look at the complete ionic equation, you have what are also known as spectator ions on both sides of the equation. So for this reaction, the nitrate is on both sides of the equation, the potassium ion are both sides of the equation. So, and these are spaced by spectators. I mean, so kind of like if you watch a sporting event, you're not really there helping out. You're not, you know, I don't know, passing the basketball. You're not catching the softball, whatever sport you're watching, right? So you're in the stands, you're the spectator. Well, I mean, I guess these are doing something. They have charges and they're floating around solutions, so that they are doing something. But as far as this chemical reaction, though, they're not really participating at all, at least in the overall reaction. So since you have the spectator ions on both sides, you can actually get rid of them, and then you can have what's known as the net ionic equation. So getting rid of the spectator ions in the complete ionic equation, you get the net ionic equation. So here's, for this chemical reaction, this is the net ionic equation. So lead 2 ion aqueous state plus 2 chloride anions aqueous state forms lead chloride precipitate. So this is your Cliff Notes or Sparks Notes, kind of thing, right? So why read Grapes of Wrath when you can read the Cliff's Notes, right? So Jodes go on holiday, or I guess they go from not holiday, Oklahoma to California, stuff happens, curious smile. That's the Grapes of Wrath, right? So this is the chemical reaction right here. Lead and 2 chlorides meet, they form a solid, story's over, kind of thing. So that's the net ionic equation. So does anybody have any questions with how this is working? So spectator ion, so look at this equation here, this net ionic equation. Silver ion plus nitrate anion plus sodium ion plus iodide anion react to form silver iodide precipitate plus nitrate plus sodium. So which one of these are the spectator ions? Or, well, if you look at the first one, silver is not a spectator ion because it's an ion here, and then it reacts. So it actually undergoes a chemical change where it forms a new compound, and you can tell there's a new compound forming because the new compound is not soluble in water. So one of the evidence of a chemical change. Nitrate, if you look at nitrate is on both sides of the equation, and it's unchanged. So nitrate is a spectator ion. So, and then iodide similar to silver, the iodide actually goes through a chemical reaction where it participates. So it's not a spectator, it's a participant. So the only one listed there, the sodium's also a spectator ion, but of the three that are listed, nitrate is the only one there that's a spectator ion. Okay. And of course, beginning of the class, we changed topics so quickly, right? So new topic. Does anybody have any questions in the old topics before we move on? Yes, please.
How do you know if it's a precipitate or not? Like
It's a solid.
do we need to clarify that? Like, will we give an aqueous and then is this going to be a precipitate?
If from previous lecture, if you were on Zoom, we talked about the solubility rules. And so we talked about how we could go and tell which ones are insoluble. If you have an insoluble compound,
That's right.
then it's a precipitation reaction.
Okay.
So we're going to talk about other types of reaction soon, like acid base is next, and then we'll talk about gas evolution reactions. And the gas evolution reaction, of course, gases bubble up. So it's like chemistry, at least taught at this level, hasn't changed since 1960. This is the old school. You take two beakers, you pour them into a bigger one, and a solid falls down. That's a precipitate. So, but people like to do the logic. So if you go on, some of these questions using charts and figures, they're found on the MCAT exam, for instance. So you won't see that in the GRE chemistry, it's too easy, but they'll put it on the MCAT. Okay, so acids and bases. So we're going to talk so much more about this later in second semester. We have a whole chapter dedicated to acids and bases, but I will just give you a real brief overview. Acids in water form hydronium ion, and bases in water form hydroxide ion. So that's the Arrhenius theory of acids and bases. You might have heard the Bronsted-Lowry, where acids are proton donors, bases are proton acceptors. And there's Lewis theory, where acids are electron acceptors, electron pair acceptors, bases are electron pair donors. We will talk about that in much greater detail. So in fact, I don't really test that much on this. I mostly do titrations for this because titrations, well, I'll show you soon about titrations. Titrations are used as a tool quite a bit to figure out how much stuff is in stuff. And some just real basic things with acids. Acids taste sour. So if you ever drank vinegar, drank citric acid, it's sour. So acids taste sour. Bases taste bitter. So things like caffeine and nicotine and many things that are poisonous, they're basic. So if you ever taste the bitter of coffee, you're tasting the alkaline. Basic and alkaline are the same thing. So they're used interchangeably. So basic alkaline things tend to be poisonous, and most humans don't like bitter things. Most humans also don't like acidic things. Humans in general tend to like sweet, salty, and the umami protein flavor. So, but generally speaking, sour and alkaline, we tend to not like those, but you can Humans can grow to like them though. So, because we're weird. But okay, talk about that much more in detail later. And acids can be polyprotic. So you see here sulfuric acid, that's H2SO4 battery acid. That has 2 protons. So it can form 2 parts acid for 1 part sulfuric acid. But here are some common acids and bases. So, well, let's see here. Let's see about chemistry and society. Does anybody know what the #1 chemical of sorts that we make as a human race with our chemical industry? So does anybody can guess what the #1 thing that we make the most of as the human race? It's transportation fuel. Oh, sorry.
Okay.
Transportation fuel. That's #1. Can anyone guess #2? Yes.
Hydrogen peroxide?
No, not even close. But it's a good guess though. Like Family Feud. Good answer. Good answer. Fertilizer. Because our agriculture is industrialized, and we use lots and lots of fertilizer. So fertilizer is #2 behind transportation fuels, and we make a lot of transportation fuels. So on Oahu, we have 100,000 barrel per day capacity to make fuel. So 100,000 barrels per day, that's 45 gallons in a barrel. That's 450,000 gallons of fuel a day that we can make. And in the state of Hawaii alone, it's probably, I think it's even more than that, but I think that's the Chevron facility. No, I'm sorry, it's a Tesaro facility. It's 100,000 barrels per day. So anyways, we make lots and lots of fertilizers, and we can make most of them from acids and bases, specifically sulfuric acid and ammonia. So that's what we really make a lot of stuff. But here are, in black, here are the strong acids. Next semester, I tell you to memorize these things. I usually don't tell you to memorize them. But to join it from the previous stuff, these are strong electrolytes. So strong acids are strong electrolytes, meaning you throw them in water and they make water conduct electricity, meaning they break apart. They completely ionize. And it's easy to tell if something's a strong acid or weak acid, because if you memorize the strong acids, every other acid's a weak acid. So there's very few strong acids. So formic acid, so it's in red. That's a weak acid. That's also the acids found in ant bites. I think I've got an ant bite on my arm, actually. I was trying to figure out what bit me. It's some of it's in bee stings too. So formis is the name for ant in Latin. So formic acid, it's antacid. Like not like anti-acid, but like the 6-legged creatures that live in colonies. Acetic acid, that's found in vinegar, it's a weak acid. And hydrofluoric acid, this is scary. I'm actually kind of a chemical phobic person, believe it or not. But hydrofluoric acid scares me. It's bone seeking. It's a surface anesthetic. Oh no, yeah, an anesthetic. You can't feel it. So if you get some, let's say you're working with it, you get some in the back of your hand, it'll start eating through to get to your bones, and you won't feel it, and you will hear kind of a sound, and you'll this happened to a friend of mine in grad school. He had like foam in the back of his hand. It was hydrofluoric acid eating his bones. So there's a cure for it. It's calcium, because hydrofluoric acid goes for calcium. You can rub calcium glutamate on it, it'll get rid of it. But it's dangerous because you can't feel it. It starts to dissolve your bones. You get bone chips in your bloodstream, cause heart attack and stroke. So scary stuff. It eats glass. So hydrofluoric acid eats glass. So it's not a very easy thing to work with. But anyways, scary stuff. Oh, if you ever see like frosted glass, how they frost the glass, they use hydrofluoric acid. So, and so now let's move on to bases. Again, I talk about it much more next semester, but sodium hydroxide, lithium hydroxide, potassium hydroxide, maybe you see a trend. There could be rubidium hydroxide next and cesium hydroxide. So the alkalis, and alkali means basic anyways. So alkali metals and then the alkaline earths. Those are some strong bases. Although I would disagree with calcium hydroxide being a strong base. I mean, you can drink the stuff if you want to, but that's my own opinion. That's, kind of like, a bunch of chemists get into a room and what we'd argue about if calcium hydroxide is a strong base or a weak base. I would consider it a weak base, but I'll go with Tro with this one. And so really the strong bases are just the alkalis and alkaline earths. And everything else is a weak base. At least that's basic. So ammonia, it's a weak base. Are there more weak acids? Are there more weak bases? Of course there are. There's many, 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 many more. So fatty acids, those are acids, right? So other things, vitamin C is ascorbic acid, anti-scurvy acid. Oxalic acid, the stuff that causes, it's in taro, causes kidney stones, right? So other weak bases. So let's see, there's nitrogen bases in DNA, adenine, thymine, guanine, cytosine. Those are all bases. Nicotine is a base, caffeine is a base, cocaine is a base, amphetamines, those are bases. Methamphetamine, amphetamine, those are bases, right? There's tons of bases. So, and on many of the words that I'm using there, they're also alkaloids. Alkaloids are plant-based basic compounds. So cocaine is an alkaloid, caffeine is an alkaloid, guanine is an alkaloid. So all these things. So anyways, you will learn much more about them later. And why are we talking about this? Because we're doing aqueous reactions and we're doing acid-base reactions. And part of it is because of titration. So we'll get to titration next. But what happens in acid-base reactions? So if you see on the left here, we have the hydronium ion. So you have this is hydrochloric acid, and it's depicted, and you can see you have the H3O plus. And so if you think of water kind of like Mickey Mouse, hydronium is like Mickey Mouse with an extra ear. And then hydroxide over here is like Mickey Mouse with only one ear, if you want to go with the Mickey Mouse analogy for water molecules. Although I must say, this is something that we're not entirely sure about. So you'll oftentimes see, oftentimes acids listed as H plus. And we've kind of all agreed it's H3O plus, but we don't really know. Meaning we can see H3O plus in solution, but hydrogen ion is just a proton, so has no electron cloud. And hydrogen ion is not something we can do spectroscopy on because there's no electrons. I mean, we can do nuclear spectroscopy, so we can do spectroscopy on the proton, but protons are not really affected by electron clouds. So a free proton is going to see the same, it will look the same nuclear-wise as a bound proton. So we just honestly just don't know if there's hydrogen ion or if there's hydronium ion. Computer simulations suggest hydronium, H3O plus. So we just kind of go with that. But truth be told, it's something in science is not, at least natural science is not considered valid until it's experimentally determined. And this is something that we really actually can't experimentally, at least not yet, we can't experimentally determine if this is true or not. So, but we just kind of go with it and say, okay, H3O plus, but then we also use it interchangeably. So you'll see it used interchangeably. In fact, I use it interchangeably. And I actually think it's easier to look at it as an H plus ion, but that comes next semester. Okay, but sodium hydroxide, this is something we are sure there is hydroxide. So that's a strong base. Both of these are strong electrolytes. And when they react, they form a salt, in this case, sodium chloride and water. And I mentioned this before. So acids taste sour, bases taste bitter. What does salt taste like? Tastes salty. So taste is a chemical process. So it tells us that sodium chloride salt is not an acid or a base. So has new chemical properties. So an acid and a base, they form a salt and water. So and that's one of the definitions of salt. Salt is the result of an acid-base neutralization reaction. Other definition of salt is metal, non-metal. That's not an oxide or hydroxide. So, okay. And let's write some of these for strong acids, strong bases. So this is a reaction between 2 hydrogen iodides plus barium hydroxide, forming aqueous barium iodide and 2 waters. So that's the molecular equation. I'm going to go ahead and write out, I already did this beforehand. Here is the net ionic equation. So the hydrogen iodide is broken up into 2 hydrogen, and I even wrote as hydrogen ions, right? So I told you can do either way. So 2 hydrogen ions plus 2 iodides, and then the barium hydroxide is 1 part barium and 2 part hydroxides. And then on the right, then you have barium and iodine as the spectator ions, and then 2 waters. So then if you look at the net ionic equation, and the net ionic equation for acids and bases is really boring because all you're forming is water, right? Because the salt is going to be soluble and it's on both sides. The metal and whatever anion is on both sides of the equation. So it's really just acid plus base makes water. I guess I can write it out. You can write it out this way as well. H3O plus aqueous plus hydroxide, aqueous, that's an ugly Q, mix to water liquid. You can write it that way as well. Or you can use H plus. They're both valid. They're actually both valid. So whichever one you prefer. So questions so far? All right, and I mentioned titrations. And I actually get into arguments with my colleagues on my opinion is very unpopular. I think that a lot of stuff we do in Chem Lab is outdated. So although we don't market it as such, right? You get a Chem Lab, and I think Chem Lab is important, but like it's a skill that no one really uses anymore. So titrations are still done. We do tons and tons of the titrations. We do many titrations here. We have a water research lab, okay? And we have a robot that does the titration. It handles something like 90 samples at the same time. So, and I mean, you load it up and you press play and you come back, you go, eat lunch, watch a couple YouTube videos, and the results are it, right? So the robot is the one that does the titration. Of course, when you're learning the stuff, you do the titration yourself. There are very, very few times that humans do the titration, but it happens. It happens some. There's sometimes. So I worked as an intern in Ecolab, and they did titrations. So did it by hand. But most of the time, though, it's robots that does it. But and again, though, chemistry at this level hasn't really changed since 1960. So you're stuck in a time loop of sorts, or not time loop. You're just kind of stuck in the 1960s. So if you ever feel like you're stuck in the 1960s in Chem Lab, that's because the same techniques that we used in the 1960s are there. We even have the Spec 20s that look like they're from the 1960s in the Chem Lab that we use. But you haven't used those yet, huh? So anyways, so titration is a way of figuring how much of something is in something. So there are many ways to do this. I mean, I just got a blood test the other day for a checkup. That's what happens when you get old. You start to get blood tests for things. And I remember looking through my results, and they showed how much sodium and potassium ions I had. I mean, I wasn't having any heart arrhythmia or anything like that, but I mean, that's one of the things they always check for. So if you go to the hospital and your heart's beating weird, they'll check your blood to see your electrolyte levels. So that's an easy thing to fix. So, and how do they figure that out? Well, they can do it by titration. I don't know what they did. I would usually use a flame test. You just stick the blood in the flame and look at the colors that come off. But that's called atomic absorption. But that's a different technique using light. But you can use wet chemical methods, and they do a lot of wet chemical methods, especially with blood, because blood's liquid. Again, though, I mean, it's not a technician, sitting in a dark laboratory, squinting at the burette. It's a robot. But one of the things that we used to use quite a bit are indicators. And you can even see, if you can see this in the screen here, I mean, it looks kind of blue, but it would be clear water. You can't really tell it's blue with this much water. But over here it's red, or pink, I should say. That's probably from phenolphthalein. So phenolphthalein has that pink color. But when you do titration, you start with something. So typically used with an acid. So well, it depends on what you're titrating. In this case, you're titrating an acid with a base, and then you get to the end point of the reaction. And so you know how much, so you know the concentration of your base. I mean, when you do a titration, you have to know one of them. So kind of like with mathematics and degrees of freedom. So if you have one equation, you can only have one unknown. So you know how much of the base you have, at least the concentration. You know the concentration, and then when you carry out the chemical reaction, you know the volume. So if you know the concentration, the volume, you know the number of moles. And if you know the number of moles, then when you have the acid, you can figure out the number of moles of acid. Well, you have to know what the identity of the acid is. If you don't know the identity of the acid, then you can figure out the number of moles equivalent, but you won't know if the acid is monoprotic, like in this case, hydrochloric acid. This is hydrochloric acid, but you don't know if it's monoprotic or diprotic like sulfuric acid, or triprotic like phosphoric. You can have tetraprotic. But anyways, so my point of this though is titrations are a way that we figure out how much stuff is in stuff. So that's another thing with chemistry, right? So let's do this for this example. You have 10 milliliters of hydrochloric acid, and it requires 12.54 milliliters of 0.1 molar sodium hydroxide. What is the concentration of hydrochloric acid? So with this, the moles of base equals the moles of acid. So when you do the chemical reaction, it helps to know the chemical reaction. So HCl plus NaOH yields NaCl plus water. So all 1 to 1 to 1 to 1. So, and we're looking for HCl in moles per liter, so the molarity. So the way that we can do this is the moles of base equals the moles of acid. So we got to figure out the moles of base. So we have 12.54 milliliters NaOH. And then we have 0.1 molar, so 0.1, oh, actually, you got to go change the liters. So it'll be liter to 1,000 milliliters. And then we have 0.1 mole NaOH per liter. And I know it's 0.1000. And the next step is going to be mole NaCl per mole NaOH. So you can do one of two ways on this. You can stop here to get the moles of hydrochloric acid, or you can just go, you can do this all in one step and just go 1 over, so 10 milliliters, and then 1,000 milliliters to liter. So this step here is kind of optional if you want, but what I'm kind of, I should put this NaOH milliliters, NaOH milliliters, HCl, because you're kind of converting back. But I'm also saying you can cross cancel terms. You can get rid of that 1,000 is where I'm going with this. So, but if you do that, and this is That's a little different than what the book does. This is me. I'm doing that all the way with dimensional analysis because I'm trying to teach you to think dimensional analysis. And if you do this, you get 0.125 molar HCl. If you stop here, that one equals 1.25 times 10 to the minus 3 moles of HCl. Then that's a C. Then you go the molarity moles. If you want to go the molarity moles per liter, this is going to be 1.25 times 10 to the minus 3 moles HCl over 0.01 liters HCl. And then you of course get the same thing. So it's sorry, I know if I teach you something, I show you another way to do it. So, but these are all valid ways. So a recap for this one, we're doing a titration, which means we're trying to figure out how much of something is in something. In this case, we want to know what the concentration of hydrochloric acid is. And so in the lab, you'll use a pipette. Pipettes are you can get a very accurate reading with them. So you pipette 10 milliliters of hydrochloric acid into your Erlenmeyer flask. You put some phenolphthalein into it. It looks clear. Then you have your burette with sodium hydroxide, and you either have the stir bar, you shake it, and you turn on the burette, and it goes down, and you find out that it turns pink after 12.54 milliliters. So you have your pink solution. You're like, all right, so I know that, but you've gone ahead and you've made the sodium hydroxide solution, so you know the concentration. And since you know the chemical reaction, you can backtrack and figure out how much hydrochloric acid in this. So by dimensional analysis, you figure out the moles of hydrochloric acid, and then you can keep on going to put in the volume, divide by the volume, or you can take the moles separately, divide by the volume, and then get the concentration. So that's how you do that. So questions with how to do this? Look here, lost in outer space. So how about the next one? How many milliliters of 1 molar sodium hydroxide are needed to neutralize 10 milliliters of 1 molar sulfuric acid? And there's a sneaky part to this one. Some people think A, 5 milliliters. I think B, 10. I think C, 20. I think D, 40. We got one going for 20. So look at the concentration. You have 1 molar and you have 1 molar, and you're neutralizing using sodium hydroxide to neutralize the sulfuric acid. So, but there is a sneakiness part to this, because it's 2 NaOH plus H2SO4 mix 2 waters plus, actually, so because sulfuric acid is diprotic, so 2 protons. So I guess I know I normally go around and talk to people, but the answer to this one is C. I'm getting some blank looks. So where are you guys getting stuck? Or was it just too fast?
Can you explain the diprotic part of it?
Okay. Explain the diprotic, and in proper form, I will give you $1 answer to a nickel question. So let's talk Mickey Mouses, right? So here is H3O plus. Right, so if you have water, here's water, there's H3O plus, here's hydroxide. So of course, so this is going to be your base, this is your acid. So if you have HCl, well, HCl plus water is going to make H3O plus Cl minus. So you're making one of these H3O pluses. When you have H2SO4, so H2SO4 plus 2 waters makes 2 H3O plus SO4 2 minus. So meaning you're going to have 2 of these weird looking 3-eared Mickey Mouse things. And the reason why you have 2 of these is because there's a 2 there. Then let's talk about phosphoric acid, H3PO4. This is triprotic. Oops, not 2. 3 HO plus PO4. So this one, this case, this is triprotic, 3 protons. So you're going to have 3. Is this helping? Okay. And there's more. I know that I'm kind of, if feels like I'm rushing through it, I kind of am, because I don't want to talk, surprisingly, I don't want to talk too much about this. You probably are never going to hear me say that about chemistry ever again, because there are so many different types of like types of acids and bases. So there's H2SO3, so sulfurous acid. There's another diprotic one, for instance. And what I'm trying to avoid is with acetic acid. Here is acetic acid. I know we haven't covered Lewis structures yet, but acetic acid is going to be C2H3CO2H, whatever. I don't know how they would write it. They would, I'll just write the structural form. CH3COOH. And this group here, this is called a carboxylic acid group. And this hydrogen, well, this bond, I haven't planned the bond. This is an easy bond to break, whereas these bonds are not easy to break. So although this molecule has 4 hydrogens, it only has 1 hydrogen that is involved in a acid-base reaction. But you learn much more about this when you get to organic chemistry. So just because a molecule has a hydrogen does not necessarily mean it's an acidic hydrogen. So that's another thing to consider. But that, of course, comes much more later. I'm sorry, here I am talking about it. For this class, it's pretty much going to be, how do I say, it's going to be pretty obvious in terms of like the acids are going to be, well, for this class, it'll give you the equation or something along the sort, so you'll know if it is diprotic or triprotic. And it's easy to tell because the monoprotic will have, it'll just have 1, the diprotic will have 2, triprotic has 3, and so on. Is this making sense, or am I talking too much and confusing you by talking too much? I'm getting the oh crap looks in your eyes. Okay.
Go back to the question you proposed.
I proposed. So how many milliliters of 1 molar sodium hydroxide are needed to neutralize 10 milliliters of 1 molar H2SO4? So I was trying to be sneaky because that's ugly. Ooh, it's even worse. Because I wanted you to realize that there are diprotic things. So you have the two hydrogens there, which means that you need two equivalents of the base to neutralize the acid.
Because the base and the acid are always 1-to-1.
No. In this case, it's 2-to-1.
Right, but to neutralize, you need like equal parts of.
Yeah. Because sodium hydroxide is going to form one hydroxide, and H2SO4 is going to form two. I'll just do hydrogen ions. H2SO4 is going to form two hydrogen ions and one SO4 anion. So sodium hydroxide forms one hydroxide, H2SO4 forms two acidic hydrogens. So because of that, you need two of these to neutralize that. So you make two waters and sodium sulfate.
And every acid base reaction always creates a water and the metals together.
And a salt.
And the salt together.
For aqueous acid-base neutralization reactions. There are some acid-base neutralization reactions that can be in the gas phase, and then you may not necessarily have that. But for aqueous acid-base reactions, yes.
Okay, yeah.
So sorry, I want to make sure that I say the correct thing. All right. Have we covered this enough, or can we move on, or you guys have more questions? What? You good? Move on. All right. Splendid answer. Okay. So new type of chemical reaction. Gas evolution reaction. And the old school way of doing things, we'd have the up arrow. So precipitate, we're down arrows, but now we use solid. Of course, if you see the up arrow, and some countries use the up arrow and the down arrow for precipitates, but they're gas evolution reactions. So this one, as written, hydrochloric acid plus sodium cyanide makes sodium chloride and hydrogen cyanide gas. So maybe an odd thing to ask, but has anyone ever smelled cyanide before? I have. It smells great, actually. Does anybody know what it smells like? Yes. It smells like almonds. It smells delicious. And if you ever somewhere, and actually almonds get their flavor from cyanide. So when you're eating, like if you've ever had, again, I guess I'm wearing the alcohol shirt. If you've ever had amaretto is distilled almonds. So it doesn't taste the same. It tastes almost like cherry, right? So when you distill it, you get rid of all the cyanide. So amaretto is kind of what almonds taste like without the cyanide. So, but cyanide, like I said, smells like almonds. And one thing about cyanide gas, your body gets used to it really fast. So if you smell cyanide, you typically, most humans only smell it for an instant and then it disappears. So I had the curse of the idiot lab partner in organic chemistry. And you usually don't smell almonds in a chem lab. And I remember my lab partner mixed acetic acid with sodium cyanide and generated hydrogen cyanide gas. And I was like, I'm sitting there in lab, I'm like, oh, almonds. I'm like, I can't smell anymore. I was like, oh, what'd you do? He's like, oh, I mixed these two things. I'm like, oh crap. And I remember remember I'm the chemistry phobic person. I went and opened the window and was breathing by the window. And I told the lab teacher, like, yeah, you're fine. And so a couple of things with cyanide. So like I said, our body's response, the dopamine response, meaning like if I'm thinking about it now, but dopamine, like if you pinch your arm, like, oh, my arm hurts, and actually I don't feel it anymore. That's because of dopamine. And there are a lot of things that happen with dopamine. When you put on your clothes, and I'm thinking about it now, I can feel my shirt move. But generally speaking, so dopamine works by stopping nerve impulses. So can you imagine what life would be like without dopamine? You're like, oh, my shirt's on, my shoes are tight, like air, wind, sound, everything. That's life without dopamine. So and we humans, when we get used to something, like I remember when I put on this mask, I was like, that's a funny smell. I'm like, no, I can't smell it. So same thing with cyanide, hydrogen cyanide gas specifically. You smell it and then it disappears. So if you are somewhere and you smell almonds out of where you shouldn't, chem lab, if you're in an industrial park and you smell almonds, and then you can't smell it after you're like, oh, almonds, like, that's weird. Don't keep running that way, turn around and run the other way. So because cyanide, it works by, it's poisonous because it binds to your hemoglobin in your blood better than oxygen, and you suffocate. So of course, if you are somewhere, say that you're in a Christmas fair and you smell almonds, you're like, I remember chemistry class, I'm smelling cyanide, I'm gonna die. No, you're not, because if roasting almonds leave a smell, the other thing is you can keep on smelling it. So you notice that when they're roasting, I love that smell of like roasting nuts. So when you smell the pure hydrogen cyanide, it disappears. So, and this is what they use in gas chambers. So that's one thing so it's a gas evolution reaction. So this is how I guess we don't typically do this anymore for executions, but this has been done in the past. Also, cyanide is used it's used for suicide pills. So you can commit suicide. Usually it's the salts though, sodium cyanide, potassium cyanide. And that's probably one of the last things you think of is like, oh, this tastes like almonds kind of thing. Oh, and be careful with certain plants. So like elderberries and bitter almonds, they have a lot of cyanide in them. So be very careful if you cook with them. So, but the nice thing I mentioned about cyanide, and my teacher was like, yeah, you're fine. Cyanide, like death happens fast. Well, at least the point of no return happens fast. With cyanide, if you can stand up and walk away, you're fine. So, I mean, the toxic level and the inability to do anything, it hits fast. So.
It has to be a lot of cyanide.
Depends on how much blood the person has, depends on, it's gonna affect children faster than adults, kind of thing. And just depends. But it's pretty low. It's actually, it doesn't require that much. And cyanides are the most toxic gas either. But the problem with cyanide, like I said, we lose the ability to smell it. It also smells good. So, I mean, hydrogen sulfide is more toxic than cyanide, but hydrogen sulfide poison is very rare because it's really smelly. So, and like hydrogen sulfide smells like rotten eggs. So, I mean, it smells worse than a wastewater treatment plant, kind of thing. I'm like, I'm okay. You're like, this smells horrible. And people just naturally move away until it's no longer toxic. Whereas cyanide, like, oh, almonds, I'm okay. I'll keep on hanging around the roasted almonds. Oh, I don't smell anymore. Well, plop. Anyways, so let's talk about other types of gas evolution reactions. I mentioned hydrogen sulfide. So if you have acids plus a sulfide, like potassium sulfide, you will form hydrogen sulfide gas and a salt. So the hydrogen sulfide, like I said, it's really toxic, smells like rotten eggs. It's in humans, we can smell sulfides in the parts per trillion range, which is really small. So we don't like it. We don't like the sulfide smell. So carbonates and bicarbonates, they make carbon dioxide. So this is the old vinegar plus baking soda reaction to make carbon dioxide. So In this case, though, we have hydrochloric acid and potassium carbonate, making water, carbon dioxide, and a salt. So maybe not potassium carbonate, but sodium carbonate. That's known as washing soda. It's the primary ingredient in OxyClean. So if you wonder what, instead of potassium, sodium. Sulfites and bisulfites. So HSO3, bi just means extra hydrogen. So carbonate is CO3, bicarbonate is HCO3, sulfite is SO3, HSO3 is bisulfite. That forms sulfur dioxide, and that's a chemical reaction there. And whenever I used to do the lab like this where we would generate them, and sulfur dioxide just gives me a horrible headache. I mean, I know the volcano pushes it out, but whenever I make this in the lab, it just gives me a bad headache. So then ammonium, forms NH3, and ammonia is weird because it can knock you out, but it can also revive you. So usually it's better at knocking you out, though, to be honest. So the old smelling salts, it's ammonium carbonate. But when you have like ammonium chloride and a base like potassium hydroxide, form water, ammonia, and a salt, and forms the ammonia gas. And I don't like the smell of ammonia. It's a really strong smell. You should, I know that you can buy ammonia at like the grocery store. You should smell the 14 molar stuff. That stuff it'll turn your head. You can't, if you smell it, it'd probably knock you out. But if you get close to it, you just kind of like naturally, it's kind of rip yourself away from it. So anyways, questions with this so far? So let me move on to the more difficult topic, oxidation reduction. So again, like I said, we changed topics yet again. So oxidation reduction. So definition of oxidation is to add oxygen is one definition. Another one is to lose hydrogen. And then the most general way of defining oxidation is the loss of electrons. So, and reduction is kind of the opposite of, well, it's not kind of, it's the opposite of oxidation. So oxidation is gain of oxygen, reduction is the loss of oxygen. Oxidation is the loss of hydrogen, reduction is the gain of hydrogen, and also reduction is the gain of electrons. So oxidation reduction, the most common oxidizing agent. Does anybody want to guess what the most common oxidizing agent is, at least here on Earth? It is oxygen. So oxygen is the most common oxidation agent. We'll talk about what causes oxidation later. Does anyone want to guess what the most common reducing agent is? Fuel and food. Well, food is fuel. So fuels so they're oxidation in general takes electrons away. Reduction in general gives electrons. So lots of chemical reactions that happen. So if you take iron, metal iron in air, it can oxidize to form iron oxide. And we can also take iron oxide and we can reduce it with carbon to form metal iron. So you can go both ways. But oxidation reduction, and if you haven't guessed already, oxidation is adding oxygen, reduction is removing oxygen. Whenever you have oxidation, you have reduction. And whenever reduction happens, you have oxidation. It's keeping track of where the electrons are flowing. And so since these reactions happen together, we call them redox reaction. Either oxidation or reduction, or we call it redox. And I guess because you could call it ox-red, but redox sounds better for some reason. So if you ever see redox, that's short for oxidation reduction. And so here are some reactions. Two hydrogen, there's actually one reaction. 2 hydrogens plus oxygen react to form water. It's a very explosive reaction. And then you have the product. And so we are then going to talk about oxidation states. And if you must know, students tend to have a hard time with this. So I was hoping to spend a little more time with this one. I guess if we have time left over, I can start looking at problems in the textbook. So oxidation states, and we start off here. Next semester, we will spend a whole chapter on electrochemistry, and we delve further into oxidation reduction reactions, specifically when it pertains to batteries. But now this is about, we're kind of building up, and this is just a way we keep track of where electrons are and where electrons are not. And these rules are also hierarchical, meaning that rule number 1 is more important than rule number 2, is more important than rule number 3. So here are the rules. Free elements, oxidation state is 0. So a monatomic ion, so mono means 1, a 1 atom ion, the oxidation state of that is equal to the charge. So I guess I should show the examples. So oxidation state, so rule number 1, a free element is 0. You can see here is copper, just metal, and chlorine, even O3, so ozone. If it's 1 element and it's all together, its oxidation state is 0. The monatomic ion is equal to its charge. So calcium +2, it's a +2 oxidation state. Chloride is a -1. And something you can kind of see where we're going with this. So an oxidation state of 0 means that the element has all of its electrons that it should have. So, and if you have a positive oxidation state, that means it's missing some electrons than it originally has. And if it has a negative oxidation state, that means it has extra electrons. So this is a way of keeping track of where electrons are. And rule number 3 is a neutral molecule. The sum of the oxidation states of all for a neutral molecule or formula unit is 0. So for water, it's 2 hydrogens, 1 oxygen, 2 times hydrogen's oxidation state plus 1 times oxygen's oxidation state equals 0, because water is neutral. And if you have an ion, the sum of the oxidation state is equal to the charge. So nitrate here, so has 1 nitrogen and 3 oxygens, and the overall has a charge of -1. A nitrogen plus 3 times the oxygen's oxidation state equals -1. So you sum those up. Rule number 4, alkalis in a compound, alkalis always have an oxidation state of +1. Alkaline earths have an oxidation state of +2. And then rule number 5, follow this chart. And here's a chart. Fluorine tends to be -1, hydrogen tends to be +1, oxygen tends to be -2, halogens tend to be -1, oxygen family tends to be -2, nitrogen family tends to be -3. So those are the general rules there. And it's hierarchical. So there's more complicated versions. You can have fractional oxidation states as well, but that's covered by different parts, different in the future. So, but for right now, we're going to stick to whole numbers. So you might see fractional oxidation states though. All right, let's do this. Anybody have any quick questions before I start doing examples? Okay. So assign the oxidation states for each atom. So chlorine, it's a free element. Oxidation state is 0. Free element, rule number 1. Sodium is a monatomic ion. Its charge is 1. It's +1. Monatomic ion is equal to charge. Then potassium fluoride. So if you do rule number 3, which means potassium plus fluorine's oxidation state equals 0. And then rule number 4, potassium is +1. So I'm just going to go ahead and put +1 there for potassium. So +1 for potassium plus fluorine equals 0. Fluorine is -1. Are you seeing my logic there? Okay. So carbon dioxide. So same with rule number 3. carbon plus 2, and I'm going to do OX for oxygen, equals 0. So carbon dioxide is a neutral molecule, and it has 1 carbon atom, 2 oxygen atoms equals 0. And if you follow the chart, then we go to rule number 4. We did number 3. The neutral molecule is 0. That was rule number 3. Number 4, alkali, alkaline earth doesn't apply. And now we're fluorine, hydrogen, oxygen. Oxygen tends to be -2. So then when we do this, it's carbon plus 2 times -2 equals 0. So I'm going to go ahead and put -2 for oxygen there. And then that means carbon equals, I know you don't have to do this, but I'm doing it for emphasis, +4. So carbon is then +4. But that kind of makes sense though, right? Because you have to have 2 -2 charges to counteract the +4 there in carbon. So question, yeah.
In the beginning, you mentioned O3.
Yeah.
And diatomic oxygen is neutral, right?
Yep.
And so O3 is also neutral?
It's a neutral, yeah.
Okay.
Yes. Free element is always 0. And unless it has an ion listed, unless it has a charge. So like here, sulfate there has a charge listed to it. So
The whole compound. Right?
yeah. So peroxide. So like you can have, so like potassium peroxide.
Mhm.
So you have O2 -2. This ion there is a peroxide. So
Right.
So you can have oxygen with a charge. But the word peroxide actually, when you say peroxide, actually means oxygen in the -1 state. So, but CO2, because there's not a charge listed, it's neutral.
And for the one you just did,
Peroxide, good, potassium, yeah.
peroxide, it was, so oxygen's -4.
K2O2. Okay, we'll do this one. So 2 times potassium plus 2 times oxygen equals 0. So in rule number 4 is potassium is +1. So you have 2 times +1 plus 2 times our oxygen state equals 0. Then you have 2 times oxygen is -2. That means oxygen is equal to -1. So oxygen can have a different oxidation state. But remember, the rules are hierarchical, meaning that rule number 4 is more important than rule number 5. So oxygen is not always going to be -2. Oxygen can be -1. And we even give it a special name. We call it peroxide. So hydrogen peroxide, oxygen is -1. Benzyl peroxide, the acne medication, -1 oxygen.
Because the oxygen element has one more electron or less than.
It's a way of keeping track of where electrons are. And it just means that in a peroxide, there's a little bit of less electron density around that oxygen atom than it likes. Oxygen is really good at drawing electron density. So peroxides tend to be reactive and or explosive. You can have something called a superoxide, which is it's when oxygen is the -1/2 state.
And can you show how O3 is a neutral?
It's just an element.
A free element.
It's a free element. It's just a diamond, carbon diamond, that's 0. Block of iron, 0. Block of lead, 0. C60, carbon 60, Buckminster fullerene, 0. So if it's one element, nothing else, no charge, it's 0. So other questions? Okay. Oh, actually, potassium peroxide is an example. Shoot. All right, I jumped ahead of myself. We'll do E then, sulfate. So we have sulfur plus 4 oxygens equals -2. So the difference here is that we have a charge. And so then as aforementioned, oxygen tends to be -2. It's not always -2, but it tends to be -2. So then I'll just go ahead and sulfur +8 is -2. Sulfur is -6. I'm sorry, +6. +6. And the other thing, you can always check this because if you sum them up, so sulfur +6 + 4 times -2 does in fact equal -2. So that's one of the ways you can always check to see if you're right. If they sum up to what they should, then you did it properly. Questions with this one so far? All right, so oxidation states in potassium dichromate. So this is a neutral unit, and you can kind of see where this is. Like you can start assigning states here. So potassium, I'll change colors. Potassium is going to be +1, and oxygen tends to be -2. So the hard one is maybe the chromium. So, well, I mean, so 2 times potassium plus 2 times chromium plus 7 times oxygen is 0. And potassium tends to be, well, is always +1, 2 times +1 plus 2 chromium plus 7 times -2 equals 0. So 2 plus 2 chromium minus 14 equals 0. 2 chromium equals 12, or chromium equals 6, specifically +6. So, and I'll go ahead and put this up here. And as you can see with oxygen, elements can have more than one oxidation state. Chromium tends to be either +3 or +6, and or 0 if it's a metal. +3 is very safe. +6 is really bad. So potassium dichromate, this stuff, it looks like yellow. It's like the minion yellow color. It's very, very bright yellow. But potassium dichromate, it's a very special chemical because it has acute toxicity, it has chronic toxicity. So it has both short-term and long-term toxicity. So this is a cancer-causing agent, so it's a carcinogen. So it's if you ever seen the movie Aaron Brockovich, it's talk about potassium dichromate. So chromium in the +6 state, sometimes called hexavalent. So if you hear the word hexavalent, chromium, that's bad. And +3 trivalent. If you hear the word valent, that usually also implies the oxidation state. So trivalent chromium is fine. We have chromium trivalent in some glasses. So like glass, like dinner, stuff that you cook cakes in or something like that. So that's safe. Hexavalent chromium is very bad. So my point is that the oxidation state does matter. It does matter because it has consequences. So let's see if you're following. What is the oxidation number of manganese and potassium permanganate? Oop, I'm blocking it with my head. There we go. Okay, so how many people think A 0? I think B 7. All right, Class is going, actually, almost everyone's going for 7. 7 is correct. All right, nice job, guys. Right, so this is +1, it's potassium, -2, so +1 plus manganese plus 4 times -2 equals 0. And that means manganese is 7. Good job. Anybody have any questions with this? But
Is there a reason why potassium is 1 again?
if you look at the hierarchy of rules, so group 1A, which is, so remember the rules are more important than as they go down. So group 1A is the alkalis. The alkalis in compounds always have an oxidation state of +1.
Oh,
And that's more important than the next rule. Well, I guess it's not necessarily the chart, but I was hoping you would follow it from potassium dichromate as well. So, other questions? Okay. And I mentioned identifying, I mentioned reducing agent and oxidizing agent. So this is kind of like backwards thinking. So so let me mime something. Here's my water bottle. And those of you on Zoom that can't see it. So I am going to be a reducing agent. I am magnesium, and I have my blue water bottle electrons. I'm gonna pick on Andre because he's in the front. And I am delivering to Andre my electron, since I don't touch my electron. So I am the reducing agent. I am delivering the electron. So since I have my electrons, I'm giving my electrons away, I have become oxidized. I've lost electrons. I've delivered electrons to the oxidizing agent. This is the person that, or the element or group of atoms that is causing the oxidation. And so what is happening to the oxidizing agent? It has gotten reduced because it has been given electrons, it is now reduced. So sorry, Zoom, you did not see the play happen, there. Okay, so hopefully you could follow by my voice. So in this reaction, I guess I should talk about the reaction. Magnesium metal is reacting with water to form magnesium hydroxide and hydrogen gas. So if you look at all the oxidation states, the free elements are 0, magnesium is 0, hydrogen in the end is 0. For water, hydrogen is in the +1 state, oxygen in the -2. And in magnesium hydroxide, magnesium is +2, oxygen is -2, hydrogen is +1. So what is changing? The magnesium is being oxidized. It is losing 2 electrons. And there are several hydrogens. 2 of the hydrogens are absorbing 1 electron each. To go from +1 to 0. And 2 of the hydrogens, nothing happens, it stays bound. So, but I mentioned, this is just a way of describing where electrons are going. So the magnesium, as I've mimed, or not, I guess I didn't mime, I guess. So by delivering my electrons, I am the reducing agent. And then the oxidizing agent, by taking the electrons away and being reduced, is delivering the oxidation. So by being oxidized, I am the reducing agent, and then the oxidizing agent, by being reduced, is delivering the oxidation. Just like James Bond, right? James Bond is the agent of death. He delivers death. He never dies himself. I've never seen a James Bond where James Bond has died, right? He's only delivering death. Just like the reducing agent is delivering reduction, and oxidizing agent is delivering oxygen or oxidation. So students do have a hard time with that, but let me see if you can see this. Glucose plus oxygen makes water and carbon dioxide. What is the reducing agents? The last topic. How many think A, glucose? How many think B, oxygen? Done. Okay, so some people one person go for oxygen. First of all, it's not going to be the products. It's only going to have to be the reactants. Do you remember what the most common reducing agents are? And what the most common oxidizing agent is? Fuel. Glucose is a fuel. It is our primary fuel. So the reducing agent is glucose. If you follow it, carbon has an oxidation of 0 and it's +4 here. Oxygen is 0 and it's going to be -2. And this is going to be +1 and this is -2. So carbon in this reaction loses 4 electrons, and oxygen here, this oxygen gains 2. So the glucose, the carbon is being oxidized. The other thing is, definition of oxidation is adding oxygen. You are literally adding oxygen to this, right? So there's a couple ways you could look at it. Oh, no, I'm over time, so I'm going to stop. So, all right. So class is over. My shut up alarm is 20 seconds past. So I'm going to, like I said, I'm going to shut up now. For real this time.